Hi, in our previous video, we finished first big part of the material, matrix algebra. And since this video, we're going to start a new part that is concerned with calculus. As I mentioned previously, calculus is the branch of mathematics that is concerned with the study of change. And look, we of course are going to be concerning the study of change in the context of the functions. But of course it can be later generalized to a lot of aspects of economics or finance, depending how you want to apply it. And look, I also told you that calculus, that we are going to do two sub-branches of calculus. And for now, we are going to concern only on differential calculus. Differential calculus concerns rates of change and slopes of the curves, slopes of the functions in general. And this is going to be the biggest part of the material we are going to cover in this class. Okay, so look, what we're going to be studying for the next couple of videos is going to be associated with the rate of change. We're going to figure out how we can measure these rates of change and how can we get some useful and very precise information about how different variables are changing. Okay, but we're going to start very slowly with the basics. Okay, so what we're going to be doing for now is a function, is a function of just one variable. So we've got y as a function of x, or y equals f of x. We know that values of y depend on values of x through some function which is usually given to us in the form of some formula. And we will be trying to relate how changes in x are affecting changes in y. And of course, if we're going to talk about change, we should start with delta. So, this is Greek letter delta, and Greek letter delta denotes change. So, if you see delta x, it is defined as, remember, every time when you see 3 bars instead of just 2, it also means that it's equal to, but it's equal by definition. So we simply say that this and this on the other hand side are the same because we define it this way. Okay, so what is delta x? Delta x by definition is x1 minus x0. Okay, but what does it mean x1 minus x0? Look, it's the best way to see it is on the axis. Okay, here we have some axis of values of x. It starts from negative infinity and it goes to positive infinity. Of course, the numbers over here are growing. So, delta x is defined as x1 minus x0. So, how do we see it in the context of change? Look, it means that at the beginning, value of x was equal to some specific number x0. And now look, how can, for some reason, now value of x is equal to x1. And look, what do we see over here? That x0 used to be here, now it's here. So it means that it has grown. By how much? Well, it has grown by delta x. And look, how can we calculate this delta x? Look, we can get it right away. If I'm going to take the bigger value, x1, and then I'm going to subtract from it a smaller value, x0, I'm going to get the size of this distance, and it will measure by how much x has changed. But look, this of course implies that in this particular scenario, delta x is bigger than 0. But it doesn't have to be this way. Look, x can grow or it can decline. And look, if we would have a different scenario in which x1 is somewhere over here, we see that x0 at the beginning was here, now it is here. So the distance between the two is equal to delta x. Now, how do we calculate it? Look, the thing is, we will calculate it in exactly the same way. Look, because we will take value of x at the end, after the decrease, and we will subtract value at the beginning. But look, this time, of course, x has declined, so we expect the delta x will be smaller than 0, because now x is lower than it used to be at the very beginning. And I think this explains in very much detail the entire idea of delta x. So generally, delta will denote change from some point x0 to some another point x1, but of course it can be for other variables, y, z, and doesn't matter. Now, every time when you see delta, it means that we are concerned with change in the value of the variable that stands after delta. Okay, now let's go back to the introduction to some basic information. Okay, look, if here we've got a y equals f of x. Look, what does it mean? Look, it means that for every acceptable value of x in the domain, we can calculate, using this formula, the value of the second variable, y, because y depends on x. Now, look, sometimes values of x that are acceptable within the function depends solely on the formula. Look, if we've got function y equals 1 over x, we clearly see that here any value is acceptable except for 0, right? X must be different than 0, or we can say the domain of the function is equal to real numbers without 0. But look, very often we are not interested in all the values. Look, for example, in economic management or financial problems, we very often need to deal with negative variables, like GDP cannot be negative, quantity cannot be negative, price actually can be negative, but this is, let's just say, a very unusual case that actually happens in the real world. But sometimes we can just restrict the values. For example, we are only interested in positive values of x. Okay, so, but what I want you to remember from that is that this gives us the entire translation of some set of x's into some different sets of y's. Now, on the other hand, you would see something like this. almost the same. I just added I next to x, right? So this means that we want to calculate the value at one specific point. Look, this is how I used 0 and 1 over here because I denoted two specific points. And this is the same I, for example, that we were considering when we were talking about sum symbol. So look, in here we've got value of the function at x, or 4 maybe, for x equal to xi, where xi is a specific number, right? So we put a specific number and we get a specific value of the function. Okay, let's practice this using a very simple example. But let's just say that our function y equals f of x is given by x squared minus 5. Okay, so what is, now let's just say, what is f of 0? Well, f of 0 is what I'm going to get out of this function if I replace x with 0. So here it would be 0 to the power of 2 minus 5, or simply negative 5. Now, if I would put here that I want to know what is f of 2, then f of 2 is what I'm going to get if I replace x with 2. So I would get that this is 2 squared minus 5, which is negative 1. Okay, I hope at this moment you understand the main difference. Like if we want to put some specific value, we just put x0, x1. If we want to know like entire range of values, we just put x. Okay, now like sometimes, very rarely, we can write, just like we written over here, that for example, y0 is equal some f of x0. And for example, that y1 is equal some f of x1. And look, this actually helps us to relate again to delta. Because look, in this context, we can say that delta y is defined as y1 minus y0, or as f of x1 minus f of x0. Very simple, right? Okay, so now we've got enough basic information to introduce the first concept, the first fundamental concept of calculus, that is called difference quotient. Okay, so the difference quotient, I hope you remember that quotient is, of course, the result of division. Difference is the result of subtraction. So, look, difference quotient is defined as quotient of two differences, because look, this is a difference, this is a difference, expressed as delta x and delta y. And in difference quotient, we divide delta y by actually, understanding how the difference quotient works is the best if we're going to put it, understanding of it is the best when we put it on a graph. Okay, so here we have y, here we have x, this is our origin, and look, let's just say that we've got some function that looks like this. Okay, and now let's see. If x at the very beginning is equal to x0, and here we will have f of x0. Then, if x then increases to some value, let's just say x1, we see that, okay, I need to extend this axis a little bit, is equal to f of x1. Okay, now, of course this line, I'm sorry, should be perfectly parallel to the horizontal axis. As I mentioned very often, I'm not a robot, so sometimes it's not coming out this way, but I hope you understand everything over here. Okay, so look, we see from this graph, at this moment we see that when x is at x0, this is the value of the function. If x is at x1, this is the value of the function. But look, as it turns out, we can write x1 in a different way. Look, how do we get this? Because, look, what is the difference between those two? Well, over here, we've got delta x. Okay, so look, if I'm going to even use this identity that delta x is equal to, okay, I'm going to write this now equal x1 minus x0, I can get x1 is equal to, if I'm going to put this on the other hand side of the equation, it turns out that x1 is equal to x0 plus delta x. What do we see over here? Look, we expressed x1 as x0 plus change in x that results in getting to x1. And look, this is a very important information because it will help us to calculate the difference quotient a little bit better. So, look, what I can do now is instead of write x1, I can simply write that this is x0 plus delta x. And look, we clearly see that this is true because this is, if this is x0, this is delta x, then this must be x0 plus delta x. Now, I can now rewrite this expression that over here we will have f of x0 plus delta x. Okay. Okay. What other things we can say? We can see over here. Look, this distance we know is delta x by how much x has changed. But look, when x has changed, as a result, f of x has changed, so y has changed. So this distance that we see over here, this was the value of y at the beginning, this is the value of y now, so this must be change in y, so delta y. Okay, knowing this, I can rewrite this difference quotient in a different way. Look, if I calculate delta y, is y y1 minus y0, or f of x1 minus f of x0. Our f of x1, so the latter value of y is given by f of x0 plus delta x. And now I just need to subtract from it f of x0. Okay. And we still divide by delta x. Okay. So look, what we get here is the proper formula for the difference quotient. Now, let me just illustrate this in a little bit different way. Let me just use like 3 different colors, and if I'm going to take this, draw a line from this point to here, from this point to here, and then from this point to here, what am I getting? What the first thing we can notice is that what I've obtained is the right-angled triangle. Now, if I denote now this this angle as alpha, what am I getting over here? Look, this line, I hope you remember, this base of the triangle is called adjacent, and adjacent is equal to delta x. Now, this line that is called the opposite is equal to delta y. Now, what is this line? Well, this is hypotenuse. We could calculate its value, for example, from Pythagoras' theorem, but this is not the thing that is important to us right now. Let me just go back for a second to a trigonometric functions that you've talked about, you probably had in high school. Look, the difference quotient is equal to delta y divided by delta x. Now, if we have a right-angled triangle, from trigonometry, we learned that if I take the opposite and I divide it by adjacent, what am I going to get? Well, I'm going to get tangent alpha. And tangent alpha, of course, is equal to delta y over delta x. And we also know that the relative length of those sizes will be connected to the angle over here and the length of this line. So look, we now can see that when we're going to be using difference quotient, we're going to be somehow using this line, the hypotenuse, to approximate the change in x. Why is it approximation? Okay, look, what is happening over here? We take the change in y and we divide it by change in x. When we do such a process, we are obtaining some average value. What is average? Okay, I assume that everybody knows what it is, but let's just remind ourselves to be sure. Okay, imagine that there are children in some school, and there is, let's just say, in one class, there is 20 children. The children brought to school candy, and some of them didn't bring candy. Some of them brought 10 candies, others brought 20, some of them bird 30. So the teacher decided that he doesn't want the children to feel left out. So he took and collected all the candy from all the children. And it turns out they had 400 pieces of candy. Now, teacher decided to divide the candy equally between all the children. So, in this case, how much candy each child should get? Well, it's quite easy to calculate, right? We take the 400 pieces of candy, and we divide it by 20 children. And now we get that this is 20. Each child should get 20 pieces of candy. So on average, we can say each of the children brought 20 pieces of candy. This is the entire idea of the average value. Okay. But now, how does this relate to a difference quotient? Look, we can pose this problem in a slightly different manner. Because, look, here we are concerned with changes. Okay, now imagine that there's an Earth Day and some boy decided to participate in cleaning Earth. And he was going to go walk 4 kilometers and collect trash that he found over these 4 kilometers, let's just say, of this road. And look, let's just say it went like this. During first kilometer, he collected 5 bags of trash. Then, during the second kilometer, he collected 4 bags of trash. Then, during the third kilometer, he collected 8 bags of trash. And then, over the next kilometer, he collected 3 bags of trash. Okay, so we clearly see that he went through 4 kilometers. During each kilometer, he collected different numbers, different quantity of bags of trash. But what we can say happened at the end? Look, at the end, we see that in total, he had 20 bags of trash. Right? If I sum up all the bags of trash, I would end up at 20. I would end up at 20 different bags. Okay. So now, look, we can think about number of kilometers as our x, and we can think about number of bags of trash that the student has collected as y. And look, what do we see? That during each kilometer, he definitely picked up a different amount of trash, different quantity of bags of trash. But look, I can still calculate a difference quotient for this situation. How? Look, here, delta y is equal to how many bags of trash he had at the beginning? 0. At the end, 20. So delta y is 20. And how many kilometers did he do? Well, at the beginning it was 0. At the end it was 4. So it's 4. And look, if I'm going to calculate difference quotient in this particular circumstance, I'm going to get that this is 5. So what does this 5 mean? It means that on average, the boy collected 5 bags of trash within each kilometer, right? Now, is it true that he collected 5 bags over everywhere? No. During the first kilometer, it is true, but look, then he collected less, then more, and then less again. But on average, we see that he actually it's like he has been collecting 5 bags of trash during each kilometer. And look, this is the information that we are getting from difference quotient, because it simply is telling us what is the change in y per unit change in x. Okay, so look, this is actually telling us how much on average the student collected bags of trash. And look, how does this relate to a function? Okay, look, we see over here that if I'm going to take and divide delta x by delta y, I will know on average over this line how the value of the function was changing per 1 unit change in x. Now, because we are using this triangle and hypotenuse over here, we are not getting precise information. Why? Look, because we can clearly see that there is some space between the two lines, which means that we are losing some information in the process. Because look, we have used a straight line to approximate this curvy line. And of course, there is a space in between them, so we are just getting average number. We are not getting the exact number. Okay, and relating this to the boy collecting trash, we clearly see that here the boy has been collecting a different amount in each kilometer. But look, if it would turn, so this is the case, like when we have a curvy line, when it does not follow a straight line. Because look, if we would be using a difference quotient for a straight line, so for example, we would have y over here, x over here, and the line would go like this, right? This is some function y equals ax plus b, right? Where here is b. Now, if I'm going to calculate difference quotient here I'm going to have some x0, here's some x0 plus delta x, and look, here we will have f of x0, here we will have f of x0 plus delta x. So, is the adjacent, so delta x. Here is the opposite, so delta y. And here is the hypotenuse that is giving our approximation. And look, now the two lines are coinciding, so the approximation is perfect. But look, this is very rarely a case. And look, we could illustrate actually a case like that with bags of trash. Look, if this boy would be collecting exactly 5 bags of trash during each kilometer, at the end he would still have 20, and the difference quotient would remain the same, right? So in this case, the approximation would be perfect. But look, in this scenario, how could we write a function of bags of trash per kilometers? Look, it would be, we could write it as number of bags of trash is equal to 5 times number of kilometers. But look, this is the same as writing the function y equals 5 times x. Okay, so look, what have we learned from this? Look, that we've learned that difference quotient is showing us average change. So it measures change in y per unit change in x. So this is only an approximation of what is really happening. Of course, this approximation is perfect in case of a straight line, but each time when the line is curvy, we will have some distortion, so measurement error. We will lose some information. Okay, so we clearly see that this measure is very nice. It brings us a lot of useful information, but this measure is by no means perfect. Okay, let me just tell you 2 additional things about a difference quotient. Difference quotient measures the average rate of change. So, as we said, if x was at the beginning 10, then it was at the beginning it was 10, at the end it was 12. Then y at the beginning, so if x0 is 10, then x1 is 12, we see that x changed by 2 units. If y0 was 7 and y2 is 11, what do we see? Look, the delta y is equal to 11 minus 7, which is 4. Delta x is 12 minus 10, which is 2. We see that on average, if x changes by 1 unit, y changes by 2 units. If this is a straight line, then we get perfect information. But if the line is curvy, we just get some approximation. Okay, and the second extremely important piece of information about difference quotient is that, look, we can think about it as a function. And look, what do we have inside this function? Look, we will have like 2 formulas, right? But those formulas are to be defined. And then we see that this function has 2 variables. In order to calculate difference quotient, we need to know 2 things. We need to know what was x at the beginning and by how much x has changed. So this is a function of two variables, x0 and delta x. Okay, so I believe that this is enough basic information about the difference quotient and how it measures the rate of change, the average rate of change. So in the next video, we're gonna start to practice it, and we actually gonna show some way how we can improve difference quotient in calculating more appropriate rate of change. And this technique is going to be called calculating a derivative. And this is going to be a subject of the next video.